All right, question 1. Given that y equals 2 plus 4 cos 3 theta, write down the amplitude of y and write down the period. Now, for all of these questions, when we've got a graph in the form y equals a cos bx plus c, or sine bx plus c for that matter, we basically need to understand what those letters a, b, and c means. And I think it's helpful to go in the reverse order. Okay, so what does c mean? C is the shift in the y direction, and it basically tells you the position of the center line of your sine or cosine graph. So what do I mean by the center line? We know that a sine graph, for example, looks like that. What I mean by the center line is this thing here, that thing there. So for example, if C is 2, then the graph is going to be centered along the line y equals 2. Okay. All right, then. What does B mean? Now, this is the one that a lot of students get confused about. They say it's the period. B is not the period. It's related to the period, but it is not the period. B is the number of waves in 2 pi radians, or in this case, in 360 degrees. So, for example, if that number is 2, it means that there are 2 waves in 360. If it's 3, it means there are 3 waves in 360. Now, what do we mean by the period? The period is how long is one wave. Okay, so if we think about it, if B was 3, what it means is there are 3 waves in 360 degrees. So how big would one wave be? It would be 360 divided by 3, right? Because if you've got 3 waves in 360, then one wave must be 360 divided by 3. So the formula that's helpful for you to remember is that the period T is equal to 360 degrees divided by that number b, all right? Or 2 pi divided by b if you're using radians. Okay, so what I want you to do is really to try to understand that, right? And please don't remember it as being the period. I think it's extremely unhelpful because it isn't the period. What it basically tells you is the number of waves in this particular amount of space, right? In 360 degrees or 2 pi radians. Okay, what's A? A is the amplitude. Okay, A is the amplitude. So if what is the amplitude? It's the distance from the center line all the way up to the top. Okay, so if I was to draw a sine wave, right, and my center line is here, so that's my center line. If I've got an amplitude of 3, what it would mean is that that height there would be 3, and that height there would also be 3. Okay, all right, well, enough of that explanation. Let's just apply it to this question. Here we've got 2 plus 4 cos 3 theta. So what's our C? Our C is 2, isn't it? So our shift in the y direction is 2. So we're going to be sent along the line y equals 2. What's our B? Our B is 3. And so that means that the period is going to be 360 divided by 3. And what's our A? Our A is 4, so our amplitude is 4. So if we just now go to this question, the amplitude of y is 4, right? 4. Okay, and what's the period of y? Well, the period of y is going to be 360 divided through by 3, right? Because 3 there is the number of waves in 360. And so therefore, we're going to get 120 degrees. Okay, so the amplitude is 4, the period is 120. Well, then part C is sketching these. Okay, so let's just go back. We said that the position of the center line is going to be y is equal to 2. Okay, so the graph is going to be centered there. We also said that the amplitude was 4, right? So it means that the graph is going to go up by 4. So 2 all the way up to 4 is going to be 6. Okay, so I'm just going to draw that as the top line. And it's going to go down by 4 from 2 to negative 2 there, right? So I've drawn my center line, and I've drawn my my peak line and my trough line. Okay, yeah, amplitude is 4. Now then, if one whole wave is 120, the period's 120, then that means our cos wave is going to start here, right? Because it always starts at the top. If it's a cos wave, if it's a sine wave, it would start there instead. And then one wave would take us 120. So we're going to end up there. Now, when you draw a sine or a cosine wave, I think the best thing for you to do is you want to divide it up into 4 equal parts. So if we've got 120 degrees for one whole cos wave, then we want to divide that into 120 divided by 4, which is 30-degree segments. So we're going to have a segment here, and here, and here. Why is that? Well, because in the first segment of the cosine wave, what you're doing is you're going from the top all the way down to the center line. Okay. In the second segment, you're going from the center line all the way down to the bottom, like that. In the third segment, you're going from the bottom all the way back up to the center line. And from the fourth segment, you're going from the center line all the way back up to the top. Okay, so I think splitting it up into 4 really helps you to get a nice smooth shape to get everything right, because basically a sine and a cosine wave can be thought of as being split up into 4 evenly spaced parts. And we're going to do the same thing here. So the first quarter takes you to there, like that. Ooh. Next quarter is going to take you down to the bottom, like that. Next quarter of the wave is going to take you to the center line. Ooh, that's not very good. Like that. And then the last one's going to take you up to the top. Okay, my drawing's not very good. I know you can see me kind of doing it with like little sketchy lines. That's not great. Obviously, if you've got a pen and paper, you would try to do it in a nice smooth curve. But in the end, what you should end up hopefully is something like that. And I hope that what I've done kind of makes sense, and you're able to draw a graph which is nice and neat. Just one final point, by the way. I noticed some students kind of draw graphs that look like that, right? That is definitely wrong. Okay, please don't do that. It's supposed to be a smooth curve. It's not supposed to have any points there. Okay, all right. I hope that was helpful. Okay, then question 2, which is a basic logarithms question. I think before we start it, let's review the logarithm rules, right? So we've got 3 key ones. Log A plus log B is log A times by B. Log A minus log B is equal to log A over B. And log A to the power of P is equal to P log A. In other words, you can take that power, bring it down to the front. Now, I think there are 2 things to note before we use these. Firstly is the bases must be the same in order for us to use those rules. So if this is log base 4 and this is log base 3, you cannot combine them like this using that log rule. The other thing is, if you're doing the first 2 log rules, and you've got a coefficient before either of these logs. Let's say this is 3 log A plus log B. You can't combine them before you deal with the coefficient. In other words, you need to take that coefficient, bring it up as a power, and then you can combine them. Okay, so those are kind of the common mistakes that I see. Let's try to do this. Well, firstly, we can combine these 2 by using the first rule, because we've got a log A plus log B. So that's going to be log base P, A times by 12, or 12A, minus log base P6. And then we can use the third log rule for this guy here, because we've got 3 log P base P4. So we can bring that 3 up as a power of 4. So I'm going to write log base P4 to the power of 3. Then I can use the second log rule for this, can't I? Because I've got log A minus log B, so that's log A over B. So I've got here log base P, 12A over 6 is equal to log base P 4 to the power of 3, which is 64. And hopefully what you can see, right, is if these 2 sides are equal, then the thing inside the logarithm must also be equal, right? In other words, what we're saying is that this guy here, 12A upon 6, must be the same as 64. So we can just write there 12A upon 6, which is the same thing as 2A, must be equal to 64. And if that's the case, A is equal to 32. Okay, so that's our answer. All right, this is part B of our logarithms questions. We want to find the exact solutions to this equation, and hopefully what you notice straight away is we've got 2 different bases. We've got a base of 3, and here we've got a base of x. So what we're going to need to do is to change the bases. So to do that, let's recap our change of base formula. If I've got log base a of x, and I want to convert it to be a log base b of the same thing, log base b of x, then I need to divide through by log base b of a, where a is the old base. So let's just think about that again. Log base a of x, if I convert it to log base b of x, I need to divide through by log base b of the old base. So let's do that here. Let's change log base x of 3 into log base 3. So if I've got log base 3 of x, and I want to convert it to log base, sorry, I got it the wrong way around there, beg your pardon. If I've got log base x of 3, and I want to convert it to log base 3, so that would give me log base 3 of 3, then I have to divide through by log base 3 of the old base, which is x, okay? So hopefully you can see what I've done over here is I've just applied that rule over there. If you're ever unsure, by the way, one of the ways you can remember is that on the right-hand side, the two bases must be the same, right? So I've got b and b here. The bases here must be the same, 3 and 3. Now, what is log base 3, 3? Log base 3, 3 is just 1. So this just gives us 1 over log base 3 of x. Okay, well then let's just apply this into our formula, or into our equation rather. We've got 4 times by log base 3 of x is equal to 9 times by 1 over log base 3 of x. And I think at this stage, it's probably best that we use a substitution. So I'm going to say let u equal log base 3 of x. And if that's the case, this equation becomes 4u is equal to 9 divided by u. And if that's the case, then we're going to get u squared is equal to 9 upon 4. And if I square root both sides, I'm going to get u is equal to plus or minus 3 upon 2. Now remember, we said that u was log base 3x. So I can write here log base 3x is equal to positive 3 upon 2. Or alternatively, log base 3x is equal to minus 3 upon 2. So if that's the case, now if we just convert both of these from logarithmic to exponential form, then x is going to be equal to 3 to the power of 3 upon 2. And here, x would be equal to 3 to the power of minus 3 upon 2. Okay, now I think that probably should be sufficient for the answer scheme. But if you wanted to convert it, you could think of it this way. You've got, what does power 3 upon 2 mean? Well, it means you've got 3 cubed, right? So that's the numerator, square rooted, right? So the power of 3 upon 2 here means you take your number, you raise it to the power of 3, and then what does the denominator of that fraction mean? It means you in this case, you square root it. So what we've got here is we've got the square root of 3 cubed. Now 3 cubed is 27, so we've got the square root of 27. And 27 is 9 times by 3. And so we can simplify that as being 3 root 3. So that may be the form that they want you to give, although that's also an exact answer. So we have to wait until the mark scheme comes out really to see. What does this guy mean? Well, it's basically saying, but what does the negative power mean? It means you've got 1 over, right? So this is 1 over the square root of 3 cubed, which is going to be 1 over 3 root 3. And we'd probably want to rationalize that. So we will get root 3 over 3 times by root 3 times by root 3, which is 3, right? So sorry, just to clarify what I've done, I multiply top and bottom by root 3, right? In order to get rid of the surd on the denominator. And root 3 times root 3 is just 3, and we times it by 3 is going to give us 9. So this answer here in the end should be root 3 over 9. Okay, all right, I hope that was helpful. Question 3. The curve C has equation y equals ln x cubed plus 3. The normal to C at the point where x is equal to 1 meets the line y equals x at the point P. Find the exact coordinates of P. Well, why don't I just quickly sketch the idea of what's going on here, just so that you kind of got a rough idea of why I'm going to do what I'm doing. Let's imagine that we've got some curve. And this isn't the curve in the question, by the way. I'll just draw like a random curve. So here's a curve there. And let's say that what we want to do is want to find the normal at this point here. Well, the tangent, right, is going to be that line, right? So something like that. What's the normal? The normal is the line that is perpendicular to the tangent. Okay, so the normal is like that line there, right? So that would be the normal at the point P. And what we're interested in is we're interested in finding where this normal line meets the line y equals x, right? Meets the line y equals x. So if I was to draw the line y equals x, that would look something like this. The question is basically asking us to find out that point there, right? So this point here is the point we're interested in. So just to clarify again, my diagram's not accurate, right? So I'm not suggesting that the curve looks like that. So let's imagine that we've got a curve here that's C. This is like the point where x is equal to 1. Okay, the green line would be the tangent to the curve at that point. And the red line is the normal to the curve at that point because it's perpendicular. And what we're asked to find is where the normal to the curve meets the line y equals x, which is that line. And so that's going to be the point that we're interested in. So how do we approach this question? Well, firstly, we need to find the equation of the normal to the curve. How are we going to find the equation to the normal at the curve? We need to know two things. We need to know the gradient of the normal, and we need to know the coordinate point. Okay, and how are we going to find the gradient of the normal? First, we need to find the gradient of the tangent. Okay, so let's try to work through all of that. So, firstly, we want to find the gradient of the tangent, so we're going to need to differentiate. How do I differentiate the natural log? Well, whatever is inside the natural log, that goes on the denominator. So we're going to put x cubed plus 3 on the denominator. And then we differentiate that, which gives us 3x squared, and we stick it on the numerator. Okay, so how do you differentiate a natural log? Take whatever's inside the natural log, put it on the denominator, differentiate that thing, stick it on the numerator. That's what's going on. Okay, so then we can use that to find the gradient of the tangent. So we can say when x is equal to 1, the gradient of the tangent, which is given by dy dx, is going to equal to 3 times by 1 squared, which is just 3, over 1 cubed, which is just 1, plus 3. So that's going to give us 3 quarters. Okay, so the gradient of the tangent is 3 quarters. Well, how can we use that to find the gradient of the normal? Well, if two gradients are perpendicular, then their product is going to equal to -1. So we know the normal is perpendicular to the tangent, so therefore the gradient of the normal is going to be -1 divided by 3 quarters, which is -4 over 3. So that's the gradient of our normal, right? So we just found the gradient of that line there. Now what we want to do is we want to find the coordinate point, the y coordinate. And how are we going to do that? Well, when x is equal to 1, when x is equal to 1, the y coordinate is going to be ln, 1 cubed plus 3, which is going to be 4. So to clarify, what we want is we want the equation now of the normal. And we know two things about that normal. We know that the gradient of the normal is equal to -4 upon 3. And we know that the coordinate point that it goes through is the coordinate 1, ln 4. Well, if we know that, then we can use our formula for the equation of a straight line, which is y minus y1 is equal to mx minus x1, where m is our gradient and x1, y1 is our coordinate point. So all I'm going to do is I'm just going to substitute in y minus ln 4 is equal to m, which is -4/3, x minus 1. Okay, so that's the equation of our normal. I'm not going to bother to rearrange it at this point because actually it may make our lives a bit more annoying. So I'm just going to leave it as it is. What are we being asked to find? We're being asked to find the intersection of that normal, right, with the line y equals x. So in other words, we're asked to solve simultaneous equations. We're asked to solve this guy simultaneously with the line y equals x, right? So kind of like we've got equation 1 here. We're solving it simultaneously with equation 2. Well, that's kind of easy. What we're going to do is we're just going to substitute y equals x into here. So let's do that. If I substitute, replace the y with the x, I'm going to get x minus ln 4 is equal to -4 upon 3 x minus 1. Okay, at this point, I probably will multiply through and expand. So I'm going to multiply everything through by 3. So that's 3x minus 3 ln 4 is equal to -4x plus 4, right? So I expanded the bracket as well. I'm going to bring all the x's through to one side. So I'm going to add 4x to both sides. That gives me 7x. and I'm going to add 3 ln 4 to both sides. That's going to give me 4 plus 3 ln 4. Yeah. And therefore, x is going to be equal to 4 plus 3 ln 4 over 7. Okay, and if that's the x coordinate, then the y coordinate is also going to be the same, right? Because y is equal to x. So the coordinate p is 4 plus 3 ln 4 over 7 for the x coordinate, and 4 plus 3 ln 4 over 7 as the y coordinate. Okay, I hope that was helpful. All right, question 4. A function f is such that f of x is equal to 2 plus e to the negative 3x for a domain of all the real numbers. I want to write down the range of f. Now, I think that with questions like this, I think they can be a little bit unhelpful in the sense they ask you to do the range first and then ask you to sketch the function later. I think it's actually easier to sketch the function because once you sketch the function, finding the range is a lot easier. So that's what I'm going to do. So I'm going to try to explain what this graph is going to look like. Now, firstly, hopefully what you know is that the graph of the exponential function y equals e to the x looks something like this, right? So it's got an asymptote on the x-axis. It cuts through the y-axis at 1, and it goes like that, right? That's y is equal to e to the x. What does e to the negative x look like? Well, it's basically the same kind of shape, but a reflection in the y-axis. So e to the negative x, slopes down like that. Okay, so that's y is equal to e to the negative x. So the basic shape of our graph here is going to look like that, right? Because we've got a negative exponential. But what's this 2 going to do? This 2 is going to shift the graph up by 2. So instead of having an asymptote at y is equal to 0 on the x-axis, all going to be shifted up by 2 coordinates. So let's try to draw that. What's going to happen to our graph? It's going to be shifted up 1, 2, 3 like that. So we're going to now have an asymptote at y is equal to 2. Bum, 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 bum. Like that. Okay. And if we wanted to double check the y-intercept is when x is equal to 0. So we just substitute that into our function. We're going to get 2 plus 2. Sorry about that. 2 plus e to the 0. And e to the 0 is 1. So the y-intercept there is going to be 3, right? So it's going to cut through there at 3. And so if we were to draw this out, then we've got the negative exponential shape. It's going to go through 3, and it's going to have an asymptote at 2. So it's going to look something like that. Okay. Now, once that's the case, we can easily find out the range, right? Because what's the definition of range? The range is all the y values that the function can take. And what we can see is that this graph, right, the y values are everything above the asymptote. It cannot be the asymptote or any value below, right? So the range is going to be y or f is greater than 2 because the graph must always be above the asymptote. It can't be greater than or equal to 2 because if it was equal, that would imply that it touches the asymptote, which it never does. Okay, then part B, we want to find an expression for the inverse. How are we going to do that? Basically, we take our function y equals 2 plus e to the negative 3x, and we rearrange it to make x the subject. So we get y minus 2 is equal to e to the negative 3x. We do the natural log of both sides. So negative 3x is equal to ln y minus 2. So x is equal to negative a third ln y minus 2. And so therefore, f inverse of x is equal to negative a third ln x minus 2, where we just replace the y with the x in the last step. Why are we doing all this, by the way? Why are we rearranging it? Well, because if you think about it, the job of the inverse function, right, is it takes the outputs from the original function, the y values, and it takes you back to the original inputs, to the x values, right? So when we're looking for the inverse function, basically what we're really asking is, given a particular y value, what was the x value that got us there, right? Given a particular output, what was the input that got us there? So that's why we're rearranging to make x the subject. All right, then, part C. we want to sketch the graphs of f of x and f inverse of x. Well, as I said, we've already kind of done this for the first function. So 1, 2, 3. We had a horizontal asymptote like that. Y is equal to 2. We had a y-intercept at 3, and the graph sloped downwards. So we had something that looked something like, sorry, this is not such a nice curve. That was our function for f. Okay, something like that. Yours should hopefully be a bit neater because, you're not doing it on the screen. Now, what about the inverse function? Well, first thing is, inverse functions are always reflections in the line y equals x. So I think it's a good idea if we just draw the line y equals x, something like that, then that's going to really help us to get a visual on what the inverse function is going to look like. So first thing, if we reflect the line y equals 2 in the line y equals x, then what we're going to get is the line x is equal to 2. Right, so we're going to have an asymptote. Instead of going through the y value of 2, it's going to go through the x value of 2. So that's going to look something like this. Let me just try to draw that. Okay. Notice that I've drawn them so that they intersect on the line y equals x. The other thing that we should see is that the x-intercept, the y-intercept at y is equal to 3 will become an x-intercept at x is equal to 3. So that's going to go there. Okay, so this guy is going to go to that. All right, then. Then what we need to do is we need to try to imagine, what's going to happen if we were to reflect the function f in the line y equals x. Okay, well, if we were to draw this, hopefully what you should be able to see is we're going to get something that's going to look like this. So first, it's got to cross over at the line y equals x. So notice there's going to be an intersection there. Okay, and then the asymptote as it goes along here, if it's reflected, is going to go along there. So we're going to have an asymptote like that. That's going to come down. That's going to cut through x is equal to 3, and it's going to go off like that. So hopefully what you can see is as you draw out these two things, that they should be reflections in the line y equals x, and that's going to be our f inverse function. Now, having said that, I think it's a good idea to think about this in a couple of ways. So I'm going to do one other thing, which I think is always helpful, which is to think about the domain and the range. Okay, so that's one trick. And we're going to do that for both f and f inverse. So for the original function f, we saw that the domain was all of the real numbers and that the range was y is greater than 2. Now, hopefully, what you should be able to understand is that for the inverse function, these two things flip, right? So the domain of the inverse function, right, this guy, is going to be the same as the range of the original function. So that's going to be x is greater than 2. In the same way, the range of the inverse function is going to be the same as the domain of the original function. So y is going to be all the real numbers. Why is that? Well, if you think about the concept of the inverse function, what it does is it undoes the function or undoes the operation of the original function. So if I was to kind of draw it out, I've got f here and f inverse, right? So I put in a value into f, I get an output value. I take that output value, I put it into the inverse function, I should get back to my original value, right? So for example, if I put 3 into the original function and got an output of 5, what that means is if I put 5 into the inverse function, I should get back to 3. What this means is that all of the outputs for the original function become the inputs for the inverse function. So it means that the range of the original function becomes the domain of the inverse, and vice versa, right? For the range of the inverse function, all the output values for the inverse function should be the same as the inputs for the original function, and that means that the range of the inverse is the same as the domain of the original. And so therefore, if we just think about this function, right? What we're saying is, since we know this must be true on the basis of this, let's just check our graph and see if it's right. What's the domain of the inverse function? The domain is x is greater than 2. And that's right, because what we see from our graph is that the x values for this inverse function are only greater than 2. Similarly, what's the domain of our inverse function? Well, it's all of the real numbers, and that's true, isn't it? Because the y values can be anything from positive infinity all the way down to negative infinity. Okay? All right, lastly, let's just think about how to sketch this. We have got the graph y is equal to negative a third ln x minus 2, wasn't it, I think? Yeah. Well, let's just say that we had to sketch this without reference to anything else. We didn't have the function to reflect. There are really two things we need to know about the logarithmic function. And that is, firstly, the thing inside the logarithm has to be positive. It has to be greater than 0. So we can say that x minus 2 must be greater than 0, and therefore x must be greater than 2. And that tells you two things, right? It tells you the domain of the function. It tells you that x must be greater than 2. And it also tells you the asymptote must be 2, right? So here what we've got is we've got an asymptote that is 2, and we know that all of our function must be to the right of that. It must be greater than 2. The second thing we can learn from this function is we can learn the x-intercept. The x-intercept is when y is equal to 0. So if I set y is equal to 0, we get 0 is equal to negative a third ln x minus 2, which means that 0 is equal to ln x minus 2. And if we were to use the exponential form, that would become e to the 0 is equal to x minus 2. E to the 0 is 1, and so x is equal to 3. So therefore, we would also be able to work out that the x-intercept is going to be here at x is equal to 3. So you should be able to work out the asymptote. You should be able to work out the x-intercept, and you should be able to have a rough idea of the shape as well on the basis of your understanding of the original function. Okay, so I've given quite a detailed explanation there, I hope. So I think it's useful to have several different ways of thinking about these questions, and I advise you to try to understand as much as you can, because ultimately when it comes to sketching a graph, what you're doing is you're piecing together all of this information in order to kind of get a coherent picture, right? So the more information you have to draw upon, the better your graph and your working is going to be. All right, last part of this functions question. A function g is such that g of x is x to the power of 3 upon 2 plus 4. For x is greater than 0, find the exact solution of this equation here. G f of x is equal to 12. Well, what does g f of x mean? It means that we take the function f of x and we put it inside of g. So it's what we call a composite function. So what we're going to do is we're going to take this function f of x and we're going to put it inside of g every time we get an x. So that's going to go there. So let's try to do that. We're going to get 2 plus e to the negative 3x to the power of 3 upon 2 plus 4. Right, so that's our function g of f of x, and we're saying that that's going to be equal to 12. So 12 is equal to this thing. And so I think the best thing there is we're just going to subtract 4 from both sides. So that's going to be 8 is equal to 2e to the negative 3x, or 2 plus e to the negative 3x to the power of 3 upon 2. Okay, then what am I going to do with that? Well, I think that I will put each power to 2 upon 3, right? So that's kind of like undoing the thing on the right, because if you think about that, 3 upon 2 to the power of 2 upon 3 is going to cancel off, just give me a power of 1. So I'm going to get here 8 to the power of 2/3 is equal to 2 plus e to the negative 3x to the power of 1. Okay, what does 8 to the power of 2/3 actually mean? Well, when you got a fraction as a power, the denominator is always telling you the root. So this is the cube root of 8. And what's this 2 on the numerator? Well, it's going to be that thing, but all squared. So if you want to think about this, what this means is we've got the cube root of 8, and then we've got that thing squared. Okay, so if you want to know the general rule, if I've got a to the power of x upon y, then that's equal to the y-th root of a all to the power of x, or that's actually the same thing as a to the power of x all to the y-th root. Okay, so that's what that power means. And that's equal to 2 plus e to the negative 3x. Okay, well, the cube root of 8 is 2. And 2 squared is 4, so 4 is equal to 2 plus e to the negative 3x. So 2 is equal to e to the negative 3x. If I was to natural log both sides, then negative 3x is going to be equal to ln 2. And divide both sides by negative 3, so x is equal to negative a third ln 2. What kind of answer are we supposed to give? I mean, that is already an exact solution. So I think that's probably going to be good enough. I mean, you could change it if you wanted to. You could write it as ln 2 to the power of negative a third, and then ln a half to the power of a third, and then 1 upon the cube root of 2. But that's already an exact solution. I think that's pretty simple. We'll wait to see what the mark scheme says, but I think that should basically be fine. Okay, then let's do question 5. The polynomial p is such that p of x is equal to this thing, where a and b are constants, and we're given that x plus 3 is a factor of both p of x and p prime of x. So we want to find the values of a and b. Okay, I think we need to just recap what the factor theorem is. And the factor theorem states that if a is a root of a polynomial f of x, then x minus a is a factor of f of x. So, for example, if 2 is a root, x minus 2 is a factor. If 5 is a root, x minus 5 is a factor. If negative 4 is a root, then x minus 4, so x plus 4 is a factor. And vice versa, right? If we know that x minus 7 is a factor, we also know that 7 is a root. So this is the key bit of knowledge here, because what we're told in the question is that x plus 3 is a factor. So what does that mean? It means that negative 3 is a root, right? Because x minus 3 is the factor. Okay, so what are we going to do? Well, I think probably first thing we want to do is why don't we just substitute in negative 3 into this guy here. So I'm going to do that. So we know that p of negative 3 is going to equal to 0. That's kind of the key fact. So I'm going to get 5 times by negative 3 cubed. So negative 3 cubed is going to be negative 27. Plus a times by negative 3 squared, which is 9. Plus 39 times by negative 3. So what's that? 40 times by 3 is 120. Minus 3 is 117, isn't it? Right? So minus 117 plus b is equal to 0. Okay, so I end up with that, and 5 times by 27, so 10 times by 27 is 270. Divide by 2 is 135. So minus 135 plus 9a minus 117 plus b is equal to 0, which means that 9a plus b is equal to 135 plus 117, so that's 245, 252, I think, 252. Yeah, that looks all right to me. Okay, then, so that's one equation that we get. Now, the next one we can do is we're going to differentiate our function. Oh, sorry about that. So if I do p prime of x, then what I'm going to get there is 15a, sorry, not 15a, 15x squared plus 2ax plus 39. And again, we're told that negative 3 is a root of this. So I can write that p prime of negative 3 is equal to 0. So if I substitute in negative 3 into that, I'm going to get 15 times by negative 3 squared, which is 9, plus 2 times by negative 3. So it's actually going to be negative 6a plus 39 is equal to 0. You know what? I think just to make my life a little bit easier, I'm going to divide everything through by 3, right? So that's going to be 5 times by 9 minus 2a plus 13 is equal to 0. And therefore, 5 times by 9 is 45. So we've got 45 plus 13, 58 minus 2a is equal to 0. So 2a is equal to 58. So a is going to be equal to 29. Okay, and if a is equal to 29, we can substitute that into here. So we've got 9 times by 29 plus b is equal to 252. Okay, so 9 times by 29. Sorry about that. 9 times by 29 plus b is equal to 252. 252, is that right? Okay, well, 10 times by 29 is 290 minus 29 plus b is equal to 252. And so what's that going to be? 290 minus 29, so minus 30 plus 1, 261. So 261 plus b is equal to 252. So b is going to equal to -9. Sorry, guys, I didn't bring my calculator today as I was doing it, but hopefully you find it helpful as well, right? You can see how I do the mental arithmetic, because if your calculator jams in an exam, that's really annoying. But hopefully it means not everything is over. Okay, so I get that a is 29, and I get that b is -9. Part B of the factor theorem question. Hence, solve the equation p of x is equal to 0 must show all your working. Well, I've just substituted in the values there for a and b that I found. And what we really want to do is want to factorize this thing fully. Now, we are told that x plus 3 is a factor. So if x plus 3 is a factor, then what we can do is we can do some polynomial division, I think. So I'm gonna take this guy here, this guy, and I'm going to divide him through by x plus 3. So let's just go on and do that. So this is x plus 3. Okay, so how do I do polynomial division? This is my leading term, right? 5x cubed. I'm going to divide that by this, divided by x. So 5x cubed divided by x is 5x squared. So I'm going to put 5x squared there. And then what I'm going to do, I'll just move this guy up so it's not so much in the way. Just move you up there. Okay. Then what I do is I take the 5x squared and I multiply it through by the entire divisor. So 5x squared times by x is 5x cubed. And 5x squared times by 3 is plus 15x squared. And hopefully what you notice, of course, is that these two guys are the same. Why do we want them the same? Because we're going to subtract the bottom equation from the top and cancel off that 5x cubed term. Now, by the way, notice that I always write my negative sign on the right. I notice a lot of students do it on the left. I think it's a really bad idea because I think it means people think this is like negative 5x cubed and this is still positive 15x squared, and they make mistakes with the minus sign. So don't do that. Avoid all confusion. Stick it over there, because what you're doing is you're taking this whole thing and subtracting it from this whole thing. All right. 15x cubed minus 15x cubed is 0. 29x squared minus 15x squared is 14x squared. And we've still got the 39x minus 9 here. Okay, then 14x squared is my new leading term. I'm going to divide that by x. So 14x squared divided by x is plus 14x. I then take the 14x, multiply it through by this entire divisor. So that gives me 14x squared plus 14 times by 3, which is 42x. And I'm going to subtract off this whole thing. And so if I do that, 14x squared minus 14x squared is 0. 39x minus 42x is minus 3x minus 9. So minus 3x becomes my new leading term. If I divide it by this x here, I get negative 3. And of course, then that gives me negative 3x minus 9, which is going to subtract off to give 0. Okay, so what do we learn? We learn that p of x can therefore be written as x plus 3 times by 5x squared plus 14x minus 3. So 5x squared plus 14x minus 3. And so that's a quadratic factor there. And we're going to see if we can factorize that guy. And if we do, it'll, oh, I don't know, actually. Let's try 5x and x. That looks to me like it'll be promising, because if I make that into a positive 3, that's going to give me 15x, and I'm going to subtract off 1x like that. That will give me 14x, and negative 1 times by 3 is negative 3. Okay, all right. You could use a calculator, by the way, or you could use the quadratic formula. Totally fine. So what we got here is we've got x plus 3, which is a repeated factor, so x plus 3 squared, times by 5x minus 1. And so our solution is going to be x equals -3 repeated. So you could put x equals -3 and -3, and then x is equal to a fifth. Now, this result here actually should make perfect sense because in the question we are told that -3 is a root of the polynomial and it's also a root of the derivative. Now, if we think about that, what does it mean? A root is where the graph cuts the x-axis, right? So that we know that our polynomial is going to cut the x-axis at -3. But we also know that since the first derivative is 0 at -3, we also know that we've got a stationary point at -3. So if we got a stationary point, it means we've either got a maximum or a minimum. Okay, now what we'll have is we'll have a maximum at this point. So what we know is at the point x is -3, we've both got an x-intercept and we've also got a maximum. So what's that going to look like? It means that the graph is just going to touch the curve at the point -3, right? So if I was to draw it out for you, if I was to draw it out like that. Okay, so imagine, so we got whatever, 1, 2, 3. So this is -3. And like here's a fifth. Okay, fifth. What I'm saying is the curve is just going to touch at -3, right? And then it'll come down, whatever, and go back up, and then cut through the x-axis again at a fifth. So this point here, if you notice, that point at -3 is simultaneously both an x-intercept and also a stationary point. And because that's the case, it is touching the curve, touching the x-axis. And when it touches the x-axis, we know that what we've got is we've got a repeated factor. So if we were being very clever, we could have said at the beginning, not only is x plus 3 a factor, but actually x plus 3 squared is a factor. And that may have simplified our working. But I think that may be perhaps a little bit, a little bit much for you guys to anticipate, but hopefully for those of you who are a bit more confident, you'll be able to see that and be able to understand it as you go. Okay. All right, then part C of this question, hence using your values for A and B, solve this particular equation here. Now the key word here is hence, isn't it? So hence means we've got to use our answer for part A and B. And I think the way to make that very clear is just use a substitution, right? Let x equal to cosec 2 theta. And if we use that, then this is going to become 5x cubed plus a, which was 29x squared, plus 39x minus 9 is equal to 0. And what we worked out in part B is that this has got two solutions. It's got solution x is equal to -3, and it had x is equal to positive a fifth. Okay, so then what we can do is we can replace our x with cosec 2 theta. So we got cosec 2 theta is equal to -3, and also cosec 2 theta is equal to a fifth. Now, what is cosec? We always look at the third letter, right? So 1, 2, 3, s. So cosec is 1 divided by sine. Okay, sec, the third letter is c, so it's 1 divided by cos, and cot, the third letter is t, so it's 1 divided by tan. So what I can do is I can now rewrite this as 1 upon sine 2 theta is equal to -3, and this is 1 upon sine 2 theta is equal to a fifth. Now, can I just highlight something? This is not sine 2 theta like that, right? So I often see that. That's the wrong way of understanding it, wrong way of writing it, because this thing is not like sine times by 2 theta, right? It's not like two things multiplied. 2 theta is going inside of the sine function. Okay, so I think it is useful. It is a good thing to have the right way of writing things. Okay, if we were to flip this fraction, we're going to get sine 2 theta is equal to -1 upon 3. And here we're going to get sine 2 theta is equal to 5. Now, of course, the sine graph only goes between plus and -1. So this guy must be rejected straight away because sine can never equal 5. So what we're trying to do is we're trying to solve sine 2 theta is equal to -1/3. All right, well, the way I always do this is I just use a substitution. I know people find that quite annoying and tedious, but I think it's just a good habit to do. So I'm going to solve sine u is equal to -1/3. Okay, And how could I do this? Well, I could use the graph of the sine function. I think that's a good way of doing it. I could also use the quadrant method or the unit circle. I mean, the quadrant method comes from the unit circle. So I think what I'll do is I'll do that. Here I've got a unit circle. Unit circle is the circle of radius 1. So let me try to draw it like that. Oh dear, that's a slightly rubbish circle. Yeah, not the best circle I've ever drawn in my life, but never mind. Let's kind of get that, like that, like that, like that, right? So that's a circle of radius 1. Now, why do we use this for trigonometry problems? Basically because for any point on the unit circle, right, that point there, which has some coordinate x and some coordinate y, which makes an angle of theta with the positive x-axis, basically the x-coordinate of this point tells you what cos theta is, and the y-coordinate of this point tells you what sine theta is, right? Or another way of putting that is, what's the definition of cos theta? It's the x-coordinate on this unit circle. And what's the definition of sine theta? It's the y-coordinate on this unit circle, right? So instead of thinking about sine and cos in terms of triangles, actually where it comes from is it comes from this circle. Okay, so if I want to find where sine is equal to negative a third, actually really what I'm asking is I'm asking where is the y-coordinate on the circle equal to negative a third. So if I was to draw that here, let's see this is negative a third. I'm going to draw a nice straight line through there. Where is the y-coordinate equal to negative a third? Well, it's going to be here, here, or here, right? So what we're really trying to do is trying to find the angles to take us to those 2 points there. All right, so let me just get rid of this. Get rid of that so it doesn't mess up our diagram a little bit. Okay, and you can find the first angle, I think, just by using your calculator. So you can find sine inverse of negative a third. And we are using degrees here, right? So it's helpful just to see that. So we're going to be using degrees. So let me just get my calculator. I need to find it first. Just 1 second. Okay, so if I do that, what I get is on the calculator is that if I do the inverse sine of negative a third, is negative 19.47. So negative 19.47. And so that's this angle here, right? Because I'm going in the opposite direction. So that's negative 19.47. Now, how could I then find this angle here? So I'll do it in yellow. So the angle that takes me from there all the way around to there, well, that's going to be 180 degrees, right? 180 degrees takes me from there to there, plus another 19.47 that takes me to there. Okay, so I'm going to do the 19.47 plus 180. Okay, so that gives me 199. So U is equal to 199.47. 0.5, isn't it? I think they ask you for one decimal place. And then how do I find this other angle? That angle there, well, that's like 360 degrees minus the 19.47, right? Because imagine I go one full rotation around my circle, then I've got to go back by 19.47. So I can do there 360 minus 19.47. So I get 340.528. So 340.5 degrees. Okay, now I need to get solutions between 0 and 360. So what I'm going to do to both of these is I'm going to add an additional 360 degrees, which on the diagram means it's like I'm going up this point, and I go around the circle another 360 degrees, so I get to the same point. The same with this guy. If I add another 360, I go around, I get to the same point. Why am I going to do that? Because remember, I need to find my value for theta. And my theta is going to be these values divided by 2. And if I take those values and I divide by 2, I may be missing out on other values here between 0 and 360. So I'm just going to add another 360 to both of these. So we got 199.5 plus the 360, which is 559. So we also got 559.5 degrees and 340.5 plus another 360 is 700.5. Okay, so these are all of my solutions for u. But remember, u is equal to 2 theta. Okay, so my theta is going to be each of these values, but then divided through by 2. So I'm going to do 199.5 divided by 2 is 99.75 or 99.8 degrees. 340.5 divided by 2, so 340.5 divided by 2, 170.3. Okay, 559.5 divided by 2, 279.8. And then lastly, 700.5 divided by 2, 350.3. Okay, so I may, by the way, by the time we don't have the mark scheme at the moment, right? So by the time the mark scheme comes out, it may be because I've rounded it here because I'm sorry, I'm using my phone as my calculator at the moment. These values may be slightly off in terms of the last decimal place. So I'm sorry about that if that's the case. But the method is essentially right. I think that the trap here that you're going to fall into, or lots of you are going to fall into, is missing out the extra solutions, right? We want theta between 0 and 360 degrees. So I think a lot of people will probably get the first value, and they may get two values, right? Oh, sorry. In this case, they'll get like 99.8 and 170.3. But there are other values for you to consider as well. Okay, so I think you just need to be a little bit careful about that. In this example, I've used the unit circle. In other examples, I use the graph of sine and cos. I hope you can try to understand what's going on with this unit circle. Effectively, what you're doing is you're exploiting the properties of symmetry. And you're also saying that if I've got 1 point on the circle that's a solution, if I add 360 to that, I'm just going to get back onto the same point, and so that's going to be another solution, right? So this guy plus 360 gives us that, and this guy plus 360 gives us that. All right, I hope that was helpful. All right, question 6. We've got a velocity time graph here. So the diagram shows the velocity time graph of a particle traveling in a straight line. The particle travels a distance of 2,750 meters in 120 seconds. Find the velocity of the particle when t is equal to 70. Look, so when you've got a velocity time graph, basically there are two facts that you need to know. You need to know that the gradient of this graph is equal to the acceleration. Okay, and if you think about that, that should kind of make sense, because what's the definition of acceleration? Acceleration is the change of velocity over the change of time. So for example, if I want to find the gradient of that line there, what would I be doing? The change of this velocity divided by the change of time, and that's the same thing as acceleration. What's the other thing you need to know? The area under the graph is equal to the displacement. Okay. Now, in this particular case, we're asked to find the distance, and sometimes we need to be careful that the distance is not the same thing as the displacement. For example, if I was to move forward 5 meters and then back 3, what would happen is my displacement would be 8, right? My distance would be 8 because I would have traveled a total of 8 meters, but my displacement would just have been 2 because I've just moved to the right by 2. Let me just try to explain that again. Right, so 0, 1, 2, 3, 4, 5. Right, imagine that I did this. I went forward 5 and then went back 3. Displacement is always the distance from the origin, right? So the displacement here would be 2, but the total distance traveled would be 8 because I moved forward 5 and back 3. So we do need to be very careful about that. But in this case, we don't need to worry. And the reason is that because the velocity is always positive, we know that we're always traveling forward, right? So if we're always traveling in the same direction, then the distance is just going to be the same thing as displacement. So in this case, the distance is just going to be equal to the area underneath this entire graph. So I know that seems like a bit unnecessary just to say, but I think just want to be careful because you're going to have to do other questions as well, and you just need to be cautious that you don't fall into any traps. All right, so what's this area going to be? The area is going to be the area of this rectangle, which is 10 times by 30, which is 300. Plus the area of this thing. Now that thing there is a trapezium, isn't it? The area of trapezium is going to be a half of this plus this. So we've got a half of 10 plus v, times by the base, which is 40. And then we've got the area of this triangle, which is going to be a half of this height times by this base. So it's going to be a half of v times by 50. So I'm going to write that down there. Plus a half v times by 50. Okay, then, well, I think I can simplify all this. We know this is going to be equal to 2750. And so that's going to be equal to 300 plus, well, a half times by 40 is 20. So if I expand the bracket, I'm going to get 200 plus 20v plus 25v. 300 plus 200 is 500. If I subtract 500 from both sides, I get 2250 is equal to 45v. And so then I've got to do 2250 divided by 45. Is that going to be 50? I think it is. Let me just double check that. 2250 divided by 45 is 50, right? So v here is equal to 50, okay? All right, then the next part of this, we want to find the acceleration of the particle when t is between 70 and 120. So that's this part of the graph, isn't it? And what I said earlier is that the acceleration is given by the gradient. So basically what we're being asked to find is the gradient of this thing. So I'll just move across to the left to do that. What's the gradient over here? Well, we can say y2 minus y1. So 0 minus v. Right, so we've got 0 minus v, which we found out was 50, over x2 minus x1, which is 120 minus 70. So we've got there 120 minus 70. So we've got negative 50 over 50, which is equal to negative 1 meters per second squared. Okay, so that should be the answer for the acceleration. It is negative. Yeah, so we're slowing down. Right, part B, a different particle moves in a straight line such that its velocity t seconds after leaving a fixed point O is given by this thing here. We want to find the exact acceleration of the particle when t is equal to 2. Well, what's acceleration? Acceleration is the rate of change of your velocity, and so it can be found by differentiating the velocity with respect to time, right? So acceleration is the rate of change of velocity, and that is exactly what dv dt means. So if we differentiate v, we should get acceleration. Now, if we're going to differentiate this function, it's helpful to notice that we've got one function multiplied by another function, right? In other words, we've got the product of two functions. And when we've got the product of two functions, we need to use the product rule. So that's what we're going to do. I'm going to call the first function u, and I'm going to call the second function v. And I'm going to differentiate both of these. So if I differentiate u, I get 1. If I differentiate v, I differentiate the big bracket first, so I get a half bracket to the power of negative a half. Then what I do is I look inside the bracket and I differentiate that. And if I differentiate t squared plus 5, I get 2t. So I'm going to multiply that by 2t. And of course, hopefully what you can see is that the half and the 2, those guys cancel off. All right, what is the product rule? The product rule is v du plus u dv, and I always remember it in that order because it's the same order as the quotient rule, and the only thing with the quotient rule is you get a negative there. Okay, so I'm just going to then substitute my values in. So if I do that, my v is t squared plus 5 to the power of a half. My u prime is 1. My u is t, and my v prime is going to be t times by t squared plus 5 to the power of minus a half. Okay, then we're asked to find the acceleration when t is equal to 2. So when t is equal to 2, the acceleration is going to be equal to 2 squared, which is 4, plus 5, which is 9. So we've got 9 to the power of a half. Plus t times by t is t squared, so that's 2 squared is 4. We've got t squared again, so that's 4 plus 5 is 9 to the power of minus a half. Okay, then what does the power of a half mean? It's the same thing as the square root of 9, so that's 3. plus 4. Now, what does 9 to the power of minus a half mean? Well, the negative in the power means we've got 1 over the square root of 9, so that's 1 upon 3. Just to go over the rules, right, if I've got a to the power of negative n, that's equal to 1 upon a to the n, okay? And also, if I've got a to the power of 1 upon m, that is the nth root of a. So those are the two rules that are being used there. Okay, so if I do that, I'm going to get 3 plus 4 thirds. Well, 3 is the same thing as 9 thirds. So I've got 9 thirds plus 4 thirds, and that is equal to 13 thirds. Okay, so 13 thirds meters per second squared, I think, should be our answer. Okay, part 2, I want to explain why the particle does not change direction. Well, I think in order to understand that, we just really need to think about what this function is going to look like. Velocity is a vector, right? So if velocity is moving that way, let's say that's the positive direction. If it starts to move in the opposite way, then the velocity would be negative, right? So in one direction, velocity is positive, and then it would be negative. So what's happening when you're changing direction? At that particular point, when you are changing direction, the velocity must be 0, right? It's what we call being instantaneously at rest. And the same is true in the other direction, right? If I imagine the particle was moving in the negative direction and it turned in the opposite direction, so it went positive. Well, again, if it's gone from negative to positive, then at this point, when it changes direction, the velocity must be equal to 0. So the core idea for you really is that if the velocity, if the particle has changed direction, right? If it's gone this way and then goes that way, or gone this way and then gone that way, it means that at that point where it changes direction, the velocity must be 0. Okay, that's the key thing. So if we now go and look at this function, we could say, well, is this ever going to be equal to 0? And the answer to that is no, because the only way it can be equal to 0 is if t itself was 0, right? If t was 0, then that would be 0 and the whole thing would be 0. But once t is just some positive number, then this is a positive number there. T squared plus 5 will be a positive number, and then you square root it, you'll get another positive number. So you've got a positive times a positive. That's always going to be a positive. It's never, ever, ever going to be 0. And so therefore, we know that since the velocity will always be positive, it will never be 0, the particle is never going to change direction. So what you need to write is something like because t is always positive, the velocity is always positive, and because velocity is always positive, we know that it doesn't change direction. Okay, so I think that's kind of the way you want to try to explain it, and the way you want to understand it. All right, question 7. We want to find this integral giving our answer in exact form. Okay, I think it should be fairly straightforward. If we integrate 5x minus 2 to the power of negative 2/3 dx between 2 and 4, how do we start that? Well, the first thing we need to do is we need to take this power and add 1. So I'm going to get over here 5x minus 2 to the power of negative 2/3 plus 1, which is positive 1/3. Then I take that power and I divide by the new power. So I'm going to divide by 1/3, and dividing by 1/3 is the same thing as timesing by 3. And then what I do is I look inside this bracket. I take the coefficient of x, which is 5, and I'm going to divide through by 5. Okay, so just to help you to see, I take that power, I add 1 to the power, I get 1/3. I divide by the new power, so I divide by 1/3, which is the same as timesing by 3. I take the coefficient of x, which is 5, and I divide by 5. Okay, and I need to remember to integrate this between my bounds, which are 4 and 2. So now what I'm going to do is I'm going to substitute in my upper bound. If I substitute in my upper bound of 4, then I'm going to get 5 times by 4, which is 20, minus 2, which is 18. So I'm going to get 18 to the power of 1/3, minus, substituting in my lower bound. So that's going to give me 3/5. So substituting 2, I'm going to get 5 times by 2, which is 10, minus 2, which is 8. So 8 to the power of 1/3. Now, what does the power of a third mean? It's the same thing as the cube root. So basically what we've got here is we've got 3/5 times by the cube root of 18 minus 3/5 times by the cube root of 8, and the cube root of 8 is 2. Okay, so I think you can probably factorize this 3/5 the cube root of 18 minus 2. And I think that should be enough for the exact form, because the cube root of 18, I don't think simplifies any further, right? For it to simplify, one of the factors of 18 would have to be a cube number, right? A cube number would be like 8 or 27, right? Or 64. And it's not. So I think the cube root of 18 minus 2 there times by 3/5 should be the simplest exact form that you're going to get. All right, part B, another integral. We want to find this integral, giving our answer in the form a plus ln b, where a and b are integers. The key thing about this is really recognizing that these two fractions are going to integrate in different ways. This fraction here is going to integrate to give a natural log, to give ln. And this fraction here is going to integrate in the same way as in part A. Now, how do you recognize that? Well, basically, if the power on the bottom of your fraction is 1, right, so this is like 2x plus 1 to the power of 1, then it integrates to give ln. If it's any other power, it's going to integrate in the usual indices way, right? So if the power on the bottom is 1, it integrates to give ln. So let me just try to do that. I'm going to rewrite this, I think. So the integral between 1.5 of 4 upon 2x plus 1 plus 8 bracket 2x plus 1 to the power of minus 2, right? So I rewrite that in indices form. The negative means 1 divided by. And what I'm saying is that this thing here integrates to give ln. Now, how does that work? Whatever's on the denominator goes inside the natural log. So we're going to write 4 ln 2x plus 1. And then what we do is we take the coefficient of the x, in this case 2, and we're going to divide through by 2. Okay. Now, the next expression, what are we going to do? We're going to add 1 to the power, so it becomes -1. We divide by the new power, so we divide by -1. Then we take the coefficient of x, which is 2, and we also divide through by 2. So let me write all of that out. This gives us 8 bracket 2x plus 1, add 1 to the power, becomes -1. We divide by that new power, so we divide by -1. And we take the coefficient of x, which is 2, we divide through by 2. Okay, and we're integrating all of this between 1/2 and 0. Well, before we carry on, I think it's a good thing to tidy up this expression. So this guy is 2 ln 2x plus 1. And we divide 8 by -2, right? So that's going to give us -4. And the 2x plus 1 to the power of -1 is 1 over 2x plus 1. And that's that there. Okay, now notice that what I did, right, is before I integrated, I converted it from like fraction form to indices form. And then once I integrated it, I converted it back to this fractional form. Now, why have I done that? Well, because I use the form that's most convenient for the operation that I'm about to do. So when I'm integrating it, it's best to have it as an indices, because then I can follow the steps logically in my head, right? Which is add 1 to the power, divide by the new power, and so on. Now what I'm going to have to do is I'm going to have to substitute these values into my into here. And so it's much easier for me, I think, to have it written out as a proper fraction, so I can cancel everything off. One of the things I notice that students do is they try to key all of this thing into the calculator, right? So you substitute in x as 1/2, they try to key it all in, including power of -1. And I think it's such a bad idea, because if you make a small error on your calculator, then you're gonna get it all wrong. So I think that the best thing for you to do is actually be nice and patient, do your working as I'm about to do, and you should get the right answer. All right. So watch me try to do it carefully. Let's substitute in 1/2. If I substitute in 1/2, I'm going to get 2 ln. 2 times by 1/2 is 1, plus 1 is 2, so that's 2 ln 2, minus 4 over 2 times by 1/2 is 1, plus 1 is 2. Okay, and then I'm going to subtract off. I'm going to substitute now the lower bound, which is 0. So I'm going to get 2 ln 1 minus 4 over 2 times by 0 is 0 plus 1. So again, what I'm going to do is I'm just going to be nice and careful, nice and slow, simplify all of this. This is 2 ln 2. 4 divided by 2 is 2 minus, now 2 ln 1, right? Ln 1 is equal to 0, so that term disappears. And 4 divided by 1 is just 4, so we've got minus 4, which is plus 4. And so then what I've got here is I have got 2 plus 2 ln 2. And let's see what form they want it in. They want it in the form a plus ln b. Well, I can use one of the logarithm rules and rewrite this as ln 2 to the power of 2, right? So I can bring that coefficient up as a power. And so therefore my final answer is going to be 2 plus ln 4. Okay, and I think that should be it. Okay, question 8, which is a permutations combination style question. A 5-digit number is to be formed using 5 different numbers selected from 1, 2, 3, 4, 5, 6, 7, 8, 9. No digit may be used more than once. Find out how many 5-digit numbers can be formed. Okay, well, we are selecting 5 digits from 9 digits and the order matters. So that answer is going to be 9p5. And if I put that into the calculator, I get 15120, right? So that's my answer there. So I'll just change that because it's a little bit messy. Now, the key issue is usually why am I using 9p5 and not 9c5? So I'm just going to try to explain that, which I usually do in the videos. What is NPR? NPR is the number of ways to arrange R items taken from N items, whereas NCR is the number of ways to choose R items taken from N items. So really the key distinction is this guy here between arranging and choosing. What's the difference? When we are arranging something, the order matters. When we are just choosing something, the order does not matter. And the key thing for you to understand is that the context is going to determine which one we're going to be using. Now, if we're making a number, and let's say that number is the number 1, 2, 3, what you need to ask yourself is that the same thing or a different thing to the number 213, right? In other words, if I take the same numbers and I rearrange them, do I get a same thing or a different thing? And in this case, this is a different thing, isn't it, right? These two are different things because the order matters. And therefore, because order matters, we're going to be using permutations and not combinations, okay? So that's the basic idea. Okay, then part 2. Find out how many of these 5-digit numbers are greater than 50,000 and even. Well, I think the best thing to do is just draw this out. 1, 2, 3, 4, 5. If we want it to be greater than 50,000, then the digit that goes there has either got to be 5, 6, 7, 8, or 9. And if it's going to be even, then the digit here can be 2, 4, 6, or 8. There's no 0. And I think it's just the best thing is just be nice and systematic, really. I'm going to cycle through the last digit. So if the last digit is 2, then how many ways could I choose that last digit? Well, it would just be 1, right? Because I've got to choose 2. There's no other choice. But if the last digit is 2, how many ways could I choose the first digit? Well, I could either be 5, 6, 7, 8, or 9. So there are 5 choices there. So there are 5 ways to choose the first digit. Well, then what about the remaining 3 digits in the middle? Well, I'm choosing 3 digits, and I'm choosing them now out of 7 digits, right? Because I started with 9 digits, but I've already chosen 2. So there are 7 digits remaining. So this is going to be 7p3, because what's going on is I am choosing 3 digits out of a total of 7 digits where the order matters, so I'm using p. Okay? All right, well then we can cycle through all the others. If the last digit is 4, then if the last digit is 4, the number of ways I can choose the last digit is 1. The number of ways I could choose the first digit is going to be 5 because of those 5 options there. And the number of ways I can choose the remaining digits is going to be 7p3. Okay, then what about if the last digit is 6? If the last digit is 6, the number of ways I can choose the last digit is going to be 1. But the ways I can choose the first digit is now going to be 4 because instead of having 5, 6, 7, 8, 9, I can no longer choose 6. And if I can no longer choose 6, then I've only got 4 options. And then how many ways can I choose the remaining 3 digits? That's 7p3. And so lastly, if the last digit is 8, then hopefully what you can see is this is going to be the same, because the number of ways I can choose the last digit is going to be 1. The number of ways I can choose the first digit has got to be 4, because I can't choose the 8. And the number of ways I can choose the remaining digits is 7p3. So what we've got is we've either got this situation, or this situation, or this situation, or this situation, right? So we've got we've got 4 possible cases to consider. So what do we got to do? We've got to add up all of these together, right? Because we're either this, or this, or this, or this. And if we've got one situation or another situation, then we need to add. So we've got 5 lots of 7p3 plus 5 lots of 7p3 plus 4 lots of 7p3 plus 4 lots of 7p3, which is 18 lots of 7p3. So 18 times by 7p3. And I'm just going to key that into the calculator. So 7p3 is 210 times by 18 is 37,800. Okay, so I think the answer for that should be 37,800. Okay, part B of our permutations combination style question. A team of 9 people is to be chosen from 6 doctors, 4 dentists, and 2 nurses. Find how many possible teams include at least 2 doctors, at least 2 dentists, and at least 2 nurses. Now, this looks like it's going to be very complicated, but actually there's one thing that you should know this is going to simplify things a lot, which is that if we need at least 2 nurses, then that means that these 2 nurses are definitely going to be included, right? So we've got no choice. We've got to include these 2 nurses. So actually, this problem simplifies quite a lot, that we've got to choose a team of 7 people now from 6 doctors and 4 dentists. Right, so immediately we can basically do away with the 2 nurses, because we know the 2 nurses have already got to be in that team of 9. So actually, really what we're choosing is we're choosing a team of 7, where we need to have at least 2 doctors and at least 2 dentists. So I think the best way to do this is then we're going to think about the different ways we can have it. So let's say we've got doctors here, and we've got dentists here, doctors and dentists. Okay, then, well, if we've got to have at least 2 doctors, let's say we had 2 doctors there, how many dentists would we need? We would need 5, wouldn't we? But hang on, we can't have that because we've only got 4 dentists to choose from. So this guy cannot exist. Okay. All right, then let's try having 3 doctors. If we had 3 doctors, then we would need 4 dentists, and that is possible, right? So that's possible. We could have 4 doctors. If we had 4 doctors, then we would need 3 dentists, and that's possible. Or we could have 5 doctors, in which case we would need 2 dentists, and that's possible. Well, then the next case would be 6 doctors and 1 dentist, but we can't have that, remember, because the condition is we must have at least 2 dentists, okay? So that's that condition there. All right, so then with this, what we need to do is we need to calculate the number of ways we can choose 3 doctors and 4 dentists, 4 doctors and 3 dentists, and 5 doctors and 2 dentists, right? So how many ways can we choose 3 doctors? Well, we're choosing 3 doctors out of 6 doctors, so that's going to be 6C3. Why are we using C? Well, because we are just choosing the doctors. The order doesn't matter. We're not arranging them. So we're using combinations, not permutations. And the same thing as if I was choosing 4 doctors, that would be 6C4. And if I was choosing 5 doctors, that would be 6C5. So how many ways then could I choose these 4 dentists? Well, I'm choosing 4 dentists from 4 dentists. So that's going to be 4C4. And then how many ways could I choose 3 dentists? That would be 4C3. And how many ways could I choose 2 dentists? That would be 4C2. And then with each of these, I'm going to be multiplying, right? Because I want 3 dentists and 3 doctors and 4 dentists. And every time we've got an and, what we do is we multiply. So this is like and, right? We've got the doctors and the dentists together, so we are multiplying. Okay. These then represent three different cases, right? We can either have this, or this, or this, right? And so because they represent three different cases, we add. So the addition there is or. Okay, so when we've got something and something, we multiply. When we've got something or something, then we add. So I think what we're going to do now is I'm just going to calculate what these values are. So 6C3 is 20, and 4C4 is 1. 6C4, so 6C4 is 15, and 4C3 is going to be 4, so times by 4 is 60, and 6C5 is going to be 6, 4C2 is 6, so that's going to be 36, and so what we're doing here then is we're going to add up all of those. So 20 plus 60 is 80, and then 80 plus 36 is 116. So I think there should be 116 ways of choosing these people. Question 9. The first three terms of an arithmetic progression, it's arithmetic, are these things here. Given that the sum to n terms of this progression is 4732 log theta, find the value of n. All right. Now, what is an arithmetic progression? An arithmetic progression is where we are adding each time, right? So if we're adding a common difference, like adding 3, adding 4, adding 5, that's an arithmetic progression. That is in contrast with a geometric progression where we are multiplying each time. Now, the thing is with this is it's going to look like we've got a geometric progression, right? Because it looks like we've got a power of 2, then a power of 5, then a power of 8. So there's going to be a trap here, which is people are going to assume wrongly that this is a geometric rather than an arithmetic progression. Okay, so you need to be a bit careful. Now, what can we do with this? Well, firstly, we can use the log rule, right? So if we've got log of a to the power of p, then that is equal to p times by log a. In other words, we can bring the power down as a coefficient. So if that's the case, then actually our progression can be rewritten as follows. It can be 2 log theta, and then 5 log theta, and 8 log theta. Okay, so I bring the powers down as coefficients. Now, when that's the case, that enables you hopefully to see two things. The first thing is, for this progression, the first term is 2 log theta. And the second thing is what we're adding each time, the common difference, is 3 log theta. Right, because 2 log theta plus 3 log theta is 5 log theta. 5 log theta plus 3 log theta is 8 log theta, right? So we've got a arithmetic progression where the first term is 2 log theta and the common difference is 3 log theta. Now we're told the sum to n terms is this thing here. So we can use our formula for the sum of the first n terms. So let me just go down. The sum of the first n terms is given by this formula, n upon 2, 2a, plus n minus 1d. And I think that's in the front of your exam booklet. So what we can do is we can just substitute our values in for this particular situation. So we've got n upon 2. Our a is 2 log theta. So what we're going to end up with here is 4 log theta plus n minus 1 times by d. And our d is 3 log theta. Now, what I'm going to do is I'm going to factorize out the log theta. So this guy is going to become n upon 2 times by log theta times by 4 plus 3 times by n minus 1. And if I do that, what I'm going to get, if I simplify that bracket, is n upon 2 log theta bracket 3n plus 1. Okay, like that. Now then, what are we told in the question? We are told that this is equal to 4732 log theta. Okay, so therefore we can say 4732 log theta is equal to n upon 2 3n plus 1. N upon 2, beg your pardon, log theta 3n plus 1. And the first thing we can see about that is that the log thetas are going to cancel, right? So I can just cancel. And basically what we're going to be left with is we're going to be left with a quadratic. So I'm going to multiply both sides by 2. I think I'll just get a calculator for that if you don't mind. So let me just open it up. 4732 times by 2 is 9464. So we got 9464 here is equal to, we'll expand this out, 3n squared plus n. And so I think what I'll do is I'll just convert that directly into a quadratic like this. Minus 9464. Now that's a quadratic, and you're going to have to solve that. So you could factorize, but I think it'd be very difficult to properly factorize that. You can use your calculator if you're familiar with using a calculator, or you could use the quadratic formula. I mean, we could use the quadratic formula, I guess, right? So n is equal to -1 plus or minus the root of b squared, which is 1 minus 4, times by a, which is 3, times by c, which is negative 9464, all over 2a, so all over 6. And we just put that into a calculator again. So 9464. Times by 12. Okay, now add 1 to it. And I think I can square root that. So let me just try to square root. Oh. Is 337. So I get -1 plus or minus the square root of 337 over 6. Now, of course, all I'm interested in is the, well, not square root of 337, beg your pardon, just 337. All I'm interested in is the positive value, right? So we can just say we've got -1 plus 337, which is 336 divided through by 6. And 336 divided through by 6 is 56. So our answer there for n should just be 56. Now, of course, you can just use your calculator, key in, but you know, a bit of practice with the quadratic formula doesn't do you any harm. Okay, second part of this arithmetic progression, we're told that this sum is equal to -14196. Find the exact value of theta. Now, you don't even need your answer for part A, right? You can just go back and look in the question. You're told that the sum to n terms is 4732 log theta. So we can just go over here and say 4732 log theta is equal to -14196. So I can take that 14196 and divide it by 4732. So let me just do that. So 14196 divided by 4732 is 3. So I get here that log theta is equal to -3. Yep, that looks right to me. And so therefore, log is log base 10, isn't it, right? So if I was to rewrite this, this is log base 10 theta is equal to -3. And then converting that to exponential form, theta is going to equal to 10 to the power of -3. And 10 to the power of -3 is 0.001, okay? Or 1 upon 1,000, right? So that should be your answer. Okay, the next part of this arithmetic geometric style question, what we've got here is a geometric progression. Now, what is a geometric progression? It's a progression in which we are multiplying each time by a common ratio. Now, I think in this particular case, again, we can use the trick that we did for the first part. I'm going to rewrite this using the logarithmic rule as 3 log phi, and a third log phi, right? So I brought the powers down as coefficients. Now, how can I find the common ratio of a geometric progression? What I'm going to do is I take the ratio of any two consecutive terms, right? So I do the second term divided by the first term, or I could do the third term divided by the second term. So what I'm going to get is I'll get log phi divided by 3 log phi. And you notice I can cancel off the log phi's like that, and I will get a third. Now then, we are asked to determine whether or not this geometric progression has got a sum to infinity. Now, what is a sum to infinity? It's a sum whereby the terms in the progression are going to get smaller and smaller and smaller, so that as you keep adding up the progression, eventually what you're going to be doing is adding on zero, adding on zero, adding on zero. So the sum is never going to grow. I think it's best illustrated with a quick example. Let's say that we had the progression 4, 2, 1, a half, a quarter, an eighth, a 16th, and so on. Now, you can imagine adding up these terms, right? So you get 4 plus 2 is 6, plus 1 is 7, plus a half, 7.5, and then 7.75, and so on. But as this progression keeps going on, you notice the terms are getting smaller and smaller and smaller and smaller. So eventually, the terms are going to be approximately equal to 0. So as you keep adding up, what's going to happen is you're going to be adding up something that's so small that it's almost 0. Well, if you've got a number and you add 0, the number remains the same, doesn't it? So in other words, the sum is going to get to a point where it's just not going to grow anymore, or not going to grow significantly. And we call that value that it reaches a limit. Okay, so it's kind of, it gets closer and closer and closer to a particular value without ever actually reaching it. And in this particular case, the limit of that progression will be 8, right? So this progression is going to get closer and closer to 8, but never actually get there. So what's the condition for this thing happening? Well, the condition is that the ratio, the term that we're multiplying by each time, has to be less than 1, because that's the condition for the subsequent terms to get smaller. So if, for example, the ratio was 2 or 3, then what's actually going to happen is each time the terms are going to double or they're going to triple. And so therefore the progression is going to grow and grow and grow, and it's not going to reach this limit, as we said, because the terms are not going to tend towards 0. Whereas if the common ratio is like a half or a quarter or 5/6, then every time we multiply, what's going to happen is the terms are going to get smaller, and eventually, if the terms are getting smaller, they're going to get to almost being 0. So essentially, we can summarize it as follows. Okay, so for a convergent series, or for a sum to infinity, the common ratio must be between -1 and 1, right? So we can also go like have negative fraction, like negative a half, negative a third. That's also fine, because what's going to happen is the terms are still going to get smaller. They're just going to flip negative, positive, negative, positive, negative, positive, right? But the key thing is that the terms themselves are getting smaller. So what can we conclude here? We can say that since a third is between -1 and 1, therefore we will have a sum to infinity. Sum to infinity. Okay, that's the key idea. All right. Now, what I suggest you do is you always want to try to understand things. So don't just memorize the condition. Try to be able to reason it out to yourself, so you can explain to yourself why this condition must be true. Right. It's always the best thing to try to understand. Okay, part 2. We want to find the nth term of this geometric progression, giving our answer in the form 3 to the power a log phi, where a is a function of n. Well, what's the nth term of a geometric progression? It's a times by r to the power of n minus 1. Okay, I think that's in the front of your exam. And what is a in this case? A is it 3 log phi? I think it was. Yeah, 3 log phi is the first term. So 3 log phi times by r. Now, the common ratio was a third, wasn't it? To the power n minus 1. Well, how could I rewrite a third? A third I could write as 3 to the power -1. So this is 3 log phi times by 3 to the power -1 to the power n minus 1. Right? So I'm using some indices rules here, right? If I've got a to the power of n, a to the power of -n, beg your pardon, then that is equal to 1 upon a to the n. And the next indices rule I'm going to use is if I've got a to the power of x times by, or to the power of y, so a to the power x to the power y, that's equal to a to the power of x times by y. So I multiply out those powers. So the next step I'm going to do is I'm going to say this is 3 times by log phi times by 3 to the power -1 times by n minus 1. So that's 3 log phi times by 3 to the power of -n plus 1. And then lastly, I can treat that 3 as 3 to the power 1, right? I can use my final indices rule, which is if I've got a to the power x times by a to the power y, that's a to the power of x plus y. I can add up the powers. So here what I'm going to get is I'm going to get 3 to the power 1 plus negative n plus 1. So that's 3 to the power of 2 minus n times by log phi. So I think we've satisfied the question because our a here, the function of n, is 2 minus n, right? So we can write a is equal to 2 minus n. Okay. All right, last part then. Find the value of phi given that the 20th term is 3 to the power of negative 18. Is that right? Well, what's the 20th term then, according to the thing we've just stated? That's going to be 3 to the power of 2 minus 20 times by log phi. And so the 20th term is going to be 3 to the power of negative 18 log phi. And so therefore we're told that the 20th term is just equal to 3 to the power of negative 18, then the conclusion that we're going to reach is that log phi is equal to 1. And then log is log base 10, right? So this is the same thing as log base 10 phi is equal to 1. Sorry, I'm just like to be clear with every step for the benefit of you guys. And so therefore phi is going to equal to 10 to the power of 1, which is just 10. Okay. All right. So I think that therefore phi should just be 10. All right. Okay. I hope that you'll find this helpful. Remember, if you have found it helpful, please like and subscribe and share with your friends.